Hey guys, it's Mrs. Stevenson, back with another lecture. The topic here is something called linear Diophantine equations. This is a number theory topic, and maybe you haven't seen this before. I have seen this come up a number of times in the high school math is cool problems. We've even seen a couple of these before down at the middle school level, so I already had this topic on my radar, but have just never had the opportunity to cover it. But I think that now is a good time. A reminder that you should have printed out this file already so that you have it available and you can take notes on it, because you're going to want to write this information down so that then you can use it, in particular the example problems, so that you can work the raffle problems, which will be due next Thursday, October 3rd. All right, so specifically, when we are talking about linear Diophantine equations, they are written in the form ax plus by equals c. Okay, and all of these values, a, b, and c, are integers. Okay, now you guys know, I mean, you could just take this and rewrite it in the form y equals mx plus b. It's just a linear equation. So we know that there are infinitely many solutions, because if you plot it, it's just a line. Any point on that line is a solution. But the key about what makes it a Diophantine equation is that we only want the integer solutions. Okay? And in particular, we are looking for the solutions x comma y, where both x and y are integers. Okay? So I think in the past, you might have seen something like this and said, okay, well, I'm just going to try to solve it using guess and check. And that could take you a really long time if you're just guessing and checking. So the point is, there's a way to solve these. There's a method, and if you follow the method, you will always be able to find the solutions. Okay? Now, just a comment that a linear Diophantine equation is solvable if and only if. If you haven't seen this before, IFF, that stands for if and only if the greatest common divisor of A and B divides into C. So just an example, if you had 3x plus 6y equals 4, well, we know the greatest common divisor of 3 and 6 is 3. That does not divide into 4 evenly. Therefore, this particular equation has no integer solutions. Okay? However, if there are integer solutions, then by definition, there will be infinitely many. Okay, not just one, infinitely, all along that line. All right, I'm going to erase this and scooch down. And let's talk specifically about the solution technique that we're going to use. Okay, so specifically, the solution technique uses something called the Euclidean algorithm. And basically, this is something we already know. If you divide an integer a by another integer b, you get a quotient and a remainder, where the remainder may or may not equal 0. So in other words, we're going to divide a by b. Okay? Well, we can write this as, well, then a is equal to b times the quotient, and then plus the remainder. Okay, so to show you an actual example with numbers, just to make it more clear, if we do 11 divided by 4, okay, so we can rewrite that as, well, 11 because 11 divided by 4, it goes into there 2 times. So 11 equals 4 times the quotient is 2, but that only makes 8. So then plus the remainder is 3. Okay? And specifically, how we're going to use this is we're going to rewrite this statement in terms of the remainder r. So we're just going to rewrite this, and we're going to solve it for r is equal to a, and then we're going to add in this times 1. And then, so for solving for r equals a, then you have to subtract b times q, right? But we're going to write it as plus b times negative q. All right, this is just part of the technique. So if I do that here with my number example, then what I would write is, so the remainder 3 is equal to a, the number we started with, 11 times 1. And then remember, we're subtracting the 4 times 2, but I'm going to write it as plus 4 times negative 2. Okay. So this is basically the technique we're going to use. We're going to do this with the equation ax plus by equals c, using a and b as the numbers, we're going to divide. And we're always going to take the larger of the two numbers. Whichever is larger, a or b, we're going to take the larger number divided by the smaller number. All right. Okay, I'm going to erase this and move on to the next page. All right, so when we do this, we are first going to end up by solving for a particular solution. When we do the technique, we will end up with specific values, x0 and y0, that solve that equation. The ax plus by equals c. If you plug in x0, y0, they will solve that equation. Then, once we have that, we're going to use those to write the general solution. So any x, which equals that particular x, x0, and then plus bn. And again, we're solving the equation ax plus by equals c. So this b is from the equation. All right, and then any y, which is equal to y0, that particular value that we found, minus a times n. Okay, where n can be any integer. So you can pick any integer n and plug it in to this set of equations, and that will give you a solution, an integer solution to this Diophantine equation. So along that line, because again, if you plot this, you get a line, pick any n, plug it in, it'll give you an integer point on that line. Pick a different n, integer, plug it in, it will give you a different integer point on that line. Okay, so that in general is how it works. All right, so I'm going to erase this, scooch up just a little, and I'm going to show you this first example. All right, so example 1. 21x plus 37y equals 1. Let's just start by finding any particular solution. So this would be A, this would be B, and then this would be C. Okay, and just notice that the greatest common divisor of 21 and 37, of course 37 is prime, so it's just 1. That divides into C equals 1, which tells us that not only is this solvable, but that there are infinite number of integer solutions. Okay, so like I said, between A and B, we always want to start with the larger divided by the smaller. So we're going to start by doing 37 divided by 21. All right, so we can write this as 37 equals, so if you do 37 divided by 21, 21 only goes into it once. So it's 21 times 1, and then the remainder is 16. Okay, and then let's just go ahead and immediately rewrite this in terms of the remainder equals stuff. So the remainder, 16, is equal to 37 times 1. And then remember, we're going to subtract, so, minus 21, but we're going to write it as plus 21 times negative 1. Okay, now we're going to keep doing this process. So we're going to look over on this side of the equation, and we're going to look at the 21 and the 16, and we're going to bring those down. Okay, and again, we're going to do the larger over the smaller. So we're just going to do it again with 21 over 16. All right, so we're doing 21 divided by 16. So 21 equals, and again, 16 only goes into it once. So it's 16 times 1, and then the remainder is 5. Okay, immediately turn around and rewrite that in terms of the remainder, 5. All right, so 5 equals, okay, the 21 times 1. And then plus 16 times negative 1. All right, we're going to do it again. So this time we have 16 and 5. We're going to bring those down. Again, we're going to take the larger over the smaller. So we're going to do 16 divided by 5. And we can write that in terms of 16 equals, so of course 5 goes into that 3 times. So it's 5 times 3, that's 15, and then of course the remainder is 1. And turn around and rewrite that in terms of the remainder. 1 is equal to 16 times 1. And then minus the 5 times 3, but we're going to write it as plus 5 times negative 3. All right, so when you get to 1 here, then we're done with this process, with this part of the process, okay? So we can stop now. So now what we're going to do is we're going to start here with the 1 equals. We're going to come down here, all right? So we're going to start, and we're basically going to work up backwards. So we have, if we bring this equation here, what we have is 1 equals 16 times 1 all right, but here's where we're going to change the equation. Notice that this whole expression here is equal to 5, and that's what we have here, 5. Okay, so what we want to do is substitute this whole expression in for 5. Okay, we're just substituting in for 5. And I'm going to put brackets around it and write it like this. So 1 equals 16 times 1 plus, and then 5 equals this whole quantity, 21 times 1 plus 16 times negative 1. Sorry, 16 times negative 1. So that is equal to 5, and then I still have the times negative 3. So this is just saying the same thing. 1 equals 16 times 1 plus 5 times negative 3. All right, now what we want to do is we want to multiply this negative 3 in. We're going to multiply it times the numbers in the parens here. Okay, so when we multiply that through, we still have 1 equals 16 times 1, and then plus, so now negative 3 times 1, so that's going to be 21 times negative 3, and then plus, okay, so the negative 3 times the negative 1, so that's 16 times positive 3. And now you might notice that we have two like terms, 16 times 1 plus 16 times 3. We can combine those. Okay, so that becomes 16 times 4 plus 21 times negative 3. All right, so still 1 equals all that stuff. Just 16 times 4 is 64, plus 21 times negative 3 is negative 63. Okay? All right, so now we're going to go back one more step. All right, we're going to go back up to this step. Okay, and notice here we have a whole expression for 16. 16 equals, let me get one more color, 16 equals all this stuff. Okay, so we're going to take all that stuff and we're going to come down here and substitute that in for 16. All right, so let's write that out. All right, so we still have 1 equals. Okay, so now I'm substituting all this. I'm going to use the bracket again. So it's 37 times 1 plus 21 times negative 1 all right, so that equals 16, and then I have the times 4. And then still the plus 21 times negative 3. All right, so just like we did before then, I want to take this 4 and I want to multiply it in. Again, I'm going to multiply it times the numbers in the parens. All right, so we're going to have 37 times 4 plus, when I multiply this, I'm going to have 21 times negative 4 plus 21 times negative 3. And just like before, notice that we have like terms here. 21 times negative 4 plus 21 times negative 3. I can combine those, and I end up with 37 times 4 plus 21 times negative 7. Okay, so now, and all of this equals 1. Now look at what we have here. And then look at what we started with up here at the very top. 21 times a number plus 37 times a number equals 1. And then look what we have here. 21 times a number plus 37 times a number equals 1. All right, I'm going to come over here to the top. Let's just put this in the same order so we have the x's and the y's the same. So we have just found out that 21 times -7 plus 37 times 4 is equal to 1. Well, that's exactly what we were trying to find. This is x, this is y. This is our particular solution. -7, 4 solves this equation. So this is our x naught, y naught. Okay, this is our particular solution. Or, I should say it is a particular solution. Because again, there are infinite solutions. So then, now that we have that particular solution, okay, just a reminder from the previous page or higher on this page that our general solution can be written as x equals x0 plus bn and y equals y0 minus an. Okay, where again, the a and b come from the original equation. This is a, this is b. So we can write our general solution for this equation as follows. X equals -7, that's our x0, plus 37n, and y equals 4 minus 21n. Okay, so in other words, we could find any other solution just by picking other values of n. Okay, so for the particular solution we just solved for, that's just equivalent to having an n of 0. Okay, because if I put n equal to 0 in here, I'm just going to get -7 and 4. But I could pick another value. Let's make it easy. Let's pick n equal 1. Okay, then x equals 37 minus 7, so x equals 30. If I put in n equals 1 here, then I got y equals 4 minus 21, which is -17. So that is another integer solution. Okay, the point 30 comma -17. Or I could pick another negative value, maybe -1n. If I do that, if I plug in -1 here, I get x is -44, and I get y is 25. All right. So there's another solution. You could pick any integer value for n and get a solution. All right, I'm going to erase all this and go on and then do one more example. Okay, erasing and going on. All right, just one more example. 7x plus 18y equals 201. And the thing I want you to notice here is that this is a little different because this isn't equal to 1. It's equal to 201. So what we will do is we will solve it exactly the same way, and then we'll deal with that 201 at the very end. And also, another requirement for this problem is Find a solution where both x and y are positive. All right, again, if we look at the GCD of 7 and 18, it's 1. That divides into 201. We know it is solvable with an infinite number of solutions. So we look at A and B. Same as before, we start with the larger 18 divided by the smaller 7. All right. So we can say that 18 is equal to, of course, 7 goes in there twice. So it's 7 times 2, that's 14. So then the remainder is 4. Okay, same as before, turn it around, rewrite it in terms of the remainder. 4 is equal to 18 times 1. And then plus 7 times negative 2. Okay, look at the numbers that are left here, the 7 and the 4. So that's going to be our new starting point for the next line. So we're going to do 7 over 4, larger over smaller always. And we can say that 7 is equal to 4 times 1, and only goes in there once, and then with a remainder of 3. Okay, rewrite that in terms of the remainder. 3 equals 7 times 1, and then plus 4 times negative 1. Okay, look at the numbers that are here, 4 and 3. That's going to be our new starting point. So we do 4 over 3, and we can say that 4 is equal to 3 times 1, and then a remainder of 1. So remember, when we hit that 1, that's when we know we can stop there. Okay. So again, rewrite this for the last time as 1 is equal to 4 times 1, and then plus 3 times negative 1. All right, so we're where we want to be, which is we have 1 equals stuff. So we're going to bring that down here. Okay. And also we're going to do exactly the same thing before. Notice that we have a 3 here and a 3 here. So we're going to take all this stuff here and substitute it in for 3. Okay, so bringing this down, we have 1 equals, so it's 4 times 1 plus, okay, substitute in all the stuff for 3. Let's put that in brackets again. So it's 7 times 1 plus 4 times negative 1. So that's the 3, and then times negative 1. Okay, multiply in that negative 1 inside the parens. All right, we're going to have 1 equals 4 times 1 plus 7 times negative 1. And then plus 4 times positive 1. Okay, combine the like terms, the 4 times 1 and the 4 times 1. So we're going to get 1 equals 4 times 2 plus 7 times negative 1. All right, come back up here. Look at the next row. We have 4 equals a bunch of stuff. So we're going to substitute all that bunch of stuff in down here for 4. So now we're going to have 1 equals Substitute all the stuff for 4. Let's put it in brackets. 18 times 1 plus 7 times negative 2. So that's the 4. And then I got to multiply that by the 2. And then plus 7 times negative 1. Okay, again, I need to distribute this multiplication here. Multiply by the numbers inside the parens. So 1 equals, all right, so this is going to be 18 times 2 plus 7 times negative 4 plus 7 times negative 1. Combine these like terms, and we're going to end up with 1 equals, okay, and then I'm just going to go ahead and put the 7 term in the front because that's the way the problem started. So we're going to have 7 times negative 5 plus 18 times 2. All right, so in other words, 7 times negative 5 plus 18 times 2 equals 1. Now, compare that, up to our starting problem. 7 times something plus 18 times something equals, okay, but we want it to equal 201, not 1. All right? So the technique here is, okay, well, let's just multiply the entire equation by 201. You can do that. We're just multiplying both sides of the equation by 201. So obviously the motivation is that on this side, we're going to end up with 201 equals stuff. Okay? Now, when we multiply this 201 in on the right-hand side, again, I'm going to multiply inside the parentheses. I want to keep that 7 and that 18. All right, again, I'm going to come up and over to the side here. All right, so I'm just going to reverse the equation as well and put this stuff on the left-hand side. So I'm going to have 7 times, okay, 201 times negative 5 is negative 1005. And then plus, and when I multiply 201 times 2, that's going to be 402. So it's plus 18 times 402 equals, and again, 201 times 1, 201. So now we have exactly what we wanted. Okay, we have 7 times an x value plus 18 times a y value equals 201. So that, the point, negative 1005, comma, 402, is our particular solution. That solves it, okay? And again, we can write our general solution. So our general solution is x equals x0 plus bn, okay? So that would be negative 1005 plus b is 18, and then times n. And then y equals, okay, y0, which is 402, minus AN. Okay, A is 7. So minus 7N. And we can pick any value of N, and then we'll get an integer solution, x comma y, to the equation. Now remember that this problem specifically asked us to find a solution where both x and y are positive. All right, so x, our particular x, is very, very negative. So the way I would tackle this is I would say, let's look at this and figure out what's the least value of n that will make x positive. So I need 18 times some number to be more positive than 1005, right? So, one way you could do that is you could just say, well, okay, what's 1005 divided by 18? In other words, how many of these 18s do I need? Okay, so I won't go through the whole division, but basically you will get 55 and then point some other stuff. So we need it to be more than that. So therefore, I need my n to be at least 56, okay, to get my x to be positive. So if we do that, if we sub in n equals 56, okay, and again, I won't go through the detailed math here, but we're just doing 18 times 56. All right, and that happens to be 1008, and then plus negative 1005. So that gives me x equals 3. And if I substitute n equals 56 into here, then I'm doing 402 minus 7 times 56. And it turns out that y then will equal 10. So that satisfies the question. That's a solution, 3 comma 10, where both x and y are positive. And also just a comment, these numbers are a lot easier and nicer. So what you can do then is you can actually rewrite your general equation if you want, just to make it easier. So we could say, oh, well, now that we have this other particular solution, we can just write, okay, x equals 3 plus 18n, and y equals 10 minus 7n. Okay, so these general solutions here are totally equivalent. All right, that's it for now. Give the practice problems a try, and again, this method always works. You just kind of have to figure out the mechanics of how to do it. All right, I'll see you guys later.